Welcome back to Fundamentals of DC Circuits. In this video, we will discuss source conversion and superposition. So the learning objectives for this video are that you will be able to demonstrate the effect of loading on a practical voltage source and a practical current source. You will be able to perform a source conversion, and you'll be able to apply the superposition theorem to circuit analysis. So let's begin with talking about the DC voltage source. Whenever we're in the lab and we're building a circuit, we're typically always using a triple power supply, which supplies a DC voltage. That's a DC voltage source. In a perfect world or in an ideal world, the ideal voltage source would deliver a constant voltage, and it also will have an internal resistance of 0. That means that when we connect something to the output of that voltage source, like a load resistor, the entire source voltage would be dropped across RL. Again, this is an ideal scenario, and in a perfect world, a DC voltage source would have no internal resistance, and therefore all of the voltage that is supplied goes directly to the load. In reality, though, no voltage source is actually ideal. All voltage sources have some sort of internal resistance that's due to the nature of how they're created. So whenever we consider a voltage source, we represent that source with an internal resistance that we call RS, which is right here. And that internal resistance could have an effect on the load that you connect to your voltage source. So with no load connected between A and B, we call that the open circuit voltage. So there'll be an open circuit voltage that'll be applied here. Once we connect the load, called RL, we'll get a voltage across RL. Again, in a perfect world, if this power supply was set to 5 volts, we'd get exactly 5 volts across RL. But because we have some internal resistance right here, that's not going to happen. There'll be a small amount of voltage drop due to this resistor here, and then the rest will be seen across RL. So what we're going to do is discuss how the internal resistance of a DC power supply can affect the voltage that can be delivered to a load. So in the first example, we're going to calculate the voltage output of the source with the following values of RL, 100 ohms and then 1 kilo ohm. So notice that the shaded box here represents our DC voltage source with an internal resistance of 10 ohms. And we're going to look how this internal resistance actually affects the voltage that you would measure across the load resistor. So let's begin with the scenario that the load resistor is 100 ohms. When the load resistor is 100 ohms, we can perform a voltage divider to figure out the voltage out across the load. We can set up that voltage divider to be 100 ohms on the top because that's the value of RL, divided by the sum of both RS and RL, which would be 100 plus 10, which is 110, and then we're going to multiply by our source voltage, which is 100 volts. So when we connect a load to this DC power supply, if it has an internal resistance of 10 ohms, I may manually set the power supply to deliver 100 volts, but what I'm really going to get out across my load is closer to 91 volts. This is how the internal resistance of a power supply can affect the output voltage that you can get to deliver to a load. Now let's consider the case where the load resistor is 1 kilo ohm. In this case, the voltage divider becomes 1 kilo ohm divided by 1.01 kilo ohms times 100 volts. Now we get an output voltage that's much closer to the source voltage. So again, if this is a DC power supply, when I set it to 100 volts, I expect to get 100 volts out. But this internal resistance is going to change that. Notice though that the larger the load, the less effect that RS has. When the load is very small, I get an output that's far less than what I put in. But when the load is significantly larger, I get an output that's only slightly less than what I put in. So the larger the load, the less that your internal resistance will affect the output voltage. This may become important whenever you're doing an experiment in a lab when you have a load that has a very low resistance. Your voltage measurements could be affected by the internal resistance of your DC power supply, and you won't really be getting the voltage that you think. So it's just something to keep in mind whenever you are using a DC power supply with a low resistance level on your load. Next, let's talk about the ideal current source. An ideal current source will produce a constant value of current through a load, regardless of the value of the load. The ideal current source has an infinite internal parallel resistance. So in a perfect world, a current source, which will just supply current the same way a voltage source supplies voltage. In a perfect world, it has an infinite amount of resistance in parallel to the current source. This is what the unloaded current source would look like, and this is what the loaded current source would look like. Here's where the load goes. And again, in a perfect world, there'd be an infinite amount of parallel resistance connected to the current source. In reality, no current source is ideal. All current sources will also have some inherent internal resistance, just like a voltage source will. So the way that we represent this is with a parallel for our internal resistance, which is Rs. We represent that in parallel with the current source, and then the load is connected between points A and B. In this scenario, if Rs is much larger than the load, as close as we can to getting to that infinite level of resistance, then the current source approaches an ideal state. However, if we have Rs that is not that much larger than the load, so again, if these two values are close in magnitude, you're going to see that your current source is not going to deliver as much current as you intended when you set up that instrument. So when we have our sources, a voltage source or a current source, we can perform what's called a source conversion. Basically, that's taking a voltage source and creating an equivalent current source or vice versa. So if you were given a voltage source, and let's say that for whatever reason you can't use a voltage source as shown here, and you need to convert that to a current source, we can simply do that using Ohm's Law. Notice that the current flowing from point A to B in this circuit has to be Vs over Rs. So our current source can simply be set to that value, Vs over Rs. And our internal resistance for Rs here will just be drawn in parallel to the current source here. This is called a source conversion. It's taking a voltage source and creating a schematic for an equivalent current source which would deliver the same amount of current and voltage to the load. The load will be connected from A to B. If I had a current source and I needed to create an equivalent voltage source, I'm simply going to use Ohm's Law in the opposite fashion. Let's say that this is the current source given and I need to create a comparable voltage source. Well, the voltage would have to be Is times Rs. That's the current flowing through the circuit times your internal resistance. So your voltage source would simply have this value, Is times Rs. And you'd now put the internal resistance in series with your DC source. That's a source conversion where you start out with a current source and you end up with an equivalent voltage source. So here's an example where we're going to convert the current source below to an equivalent voltage source, and then we'll show what the equivalent circuit looks like. So again, to do this, you're simply going to apply Ohm's Law. The voltage for your equivalent source has to be the source current here times the internal resistance here, which gives you 10 volts. So your equivalent circuit will look like this, where I have a 10 volt source instead of a 10 milliamp source, and our internal resistance is now in series with the voltage source instead of in parallel with the current source. That's what a source conversion is. If I have a voltage source and I need to convert it to an equivalent current source, I'll simply use Ohm's Law again, but in the opposite fashion. I'll calculate the current that must be available from this circuit by doing Vs over Rs. And then I'm going to draw an equivalent diagram which shows that current source with that value of current and the internal resistance in parallel to the current source. Keep in mind the direction of current here should match the direction that current flows in the original picture. I use the polarity of the DC source to know which way the current will flow. If this symbol happened to be flipped upside down and the plus sign was at the bottom, then your arrow for your current source would have to be pointing down. Next, we're going to move on to a new theorem called the Superposition Theorem. Some circuits use more than one voltage or one current source. The Superposition Theorem provides a method to determine the current in a circuit that has multiple sources. All the sources will be treated as an ideal source to simplify the application of this theorem. Here's the basics of the Superposition Theorem. Let's say that you begin with a circuit that has 2 voltage sources, or 3 voltage sources, or 2 voltage sources and 1 current source, or any combination of those. What you're going to do is leave one source, either a voltage source or a current source, it doesn't matter. You're going to leave one at a time and replace all others with a short circuit if it's a voltage source, or an open circuit if it's a current source. Then you're going to go find a particular branch current as if there was only one source in the circuit. So you're going to eliminate all sources but one and find the current that you're looking for. Then you're going to repeat this by replacing a different voltage source or current source with open circuits or short circuits depending on the source. And you're going to repeat this process for each source in the circuit. When you're done, you're going to algebraically sum the individual currents that you found to determine the total current in the branch. This means that the direction of current flow must be considered. We're doing an algebraic sum. Anytime you have to do an algebraic sum, you must consider polarity or direction of current flow. So that's going to be very important as we learn how to apply the superposition theorem. So we'll start by looking at an example. But before we can do that, let's make sure that we have clearly defined what an open circuit and a short circuit is. An open circuit has a broken current path, which does not allow current to flow. So in this example here, this is a closed circuit. Current is able to flow through the entire circuit. If we have an open filament right here, this creates an open circuit. Current can flow through here, it gets here and does not have a path to continue. This is considered an open circuit, and there is no current flowing in this circuit. Same thing down here. If we have a missing resistor right here, there's literally no connection, no wire, no anything between R3 and R5. And in this case, that would create an open circuit, and then there is no current flowing through any of these resistors while this is open. That's an open circuit. A short circuit has an additional path that is non-resistive, meaning there's no resistance along that path. It's simply a wire for current to flow. Current will always follow a path of non-resistance, causing more current in a circuit than normal. So here's an example. Here's a basic circuit here. We've got an ammeter to measure the current, and we've got a few resistors in series. And the current in this circuit is 1 amp. Let's say that I add a short circuit, meaning I put a wire from this point to this point. What's going to happen is the current, get my highlighter, the current is going to flow through the ammeter, through the 10 ohms, through the 18 ohms, and then through the short. The current will never flow through these two resistors here because current will always take a path of non-resistance. So the current is going to follow this path. So this path has less resistance because you've cut these two out, which drives your current up. This circuit may not have ever been intended to have that much current, so a short circuit can be a huge problem because it creates more current than normal in a circuit. So that's what a short circuit is. So as we use the superposition theorem, we will be replacing voltage sources and current sources with either a short circuit or an open circuit, depending on the source. Again, if it's a voltage source, it's going to become a short circuit. If it's a current source, it's going to become an open circuit. And now we'll do some examples to demonstrate this theorem. For For the first example, we're going to find the current through R2. Here's R2. In this case, we have a 10-volt source right here. We have a 5-volt source right here. And we have 3 resistors that are neither in series nor in parallel. So we can't really do anything with this circuit as is. You, at this point in the course, have no tools with which to analyze a circuit like this that has 2 sources. The superposition theorem is your first tool that you're going to learn to help you figure out how to find the current through R2, given that there are 2 voltage sources in this circuit. So, to begin, you're going to select a source. It doesn't matter which one you pick, either this one or this one, and replace it with a short. So you're going to pick a voltage source and replace it with a short circuit. And then you're going to find the current through R2. So I am going to take voltage source 2 and replace it with a short circuit. That means my picture now looks like this. So any voltage source that gets replaced with a short circuit basically gets replaced with a wire. Now I only have one source, and I'm going to find the current through R2. In order to do that, I need to find the total resistance in the circuit. The total resistance in the circuit is going to be these 2 in parallel plus R1. Once I combine these two will be in series with R1. So I'm going to find the total resistance by combining these in parallel and adding R1 to it. That gives you a total resistance of 150 ohms in the circuit. Then I can go find the total current, which would be 10 volts divided by 150 ohms, giving me 66.67 milliamps. Now I know the total current that flows from the source and into that node, and then it'll split. I need to know how much will go through R2. So I'm going to do a current divider. The current divider has to have this parallel combination on the top. So these 2 combined in parallel gives you 50 ohms. Then I'm going to divide by the value of R2, which is 100 ohms. And then I'm going to multiply by the total current going into the node, which is 66.67 milliamps. So I end up with the current through R2 coming out to be 33.35 milliamps. And this is very important. You must write down the direction of the current, because at the end of this problem, we have to algebraically sum each current that we have found, and you have to know the direction in order to do that. So make sure that you indicate that the current is flowing down in this case. Now we're going to repeat this process, but we're going to put VS2 back and then short VS1 and do the exact same thing that we just did. So we're going to replace the first voltage source, put it back into the circuit, and short the other voltage source, and then find the same current going through R2. There's my short. The first voltage source is now gone, and I have to do the same thing as before, find the current through R2. In order to do that, I'm going to have to start with finding the total resistance of this circuit. Now keep in mind, the total resistance came out to be the exact same value, but that's coincidence only. That came out to be the same value because these are all the same value here. Notice that if I have replaced VS1 with a short and I bring back VS2, R1 and R2 are now what are in parallel. Before, R2 and R3 were in parallel. So don't let this number fool you. Look at the circuit very carefully. R1 and R2 are in parallel, and then that parallel combination is in series with R3. This is how we get a total resistance of 150 ohms. Next, we can find the total current in the circuit, which will be 5 volts divided by 150 ohms. That'll give you 33.33 milliamps. So now we know that the total current in the circuit is flowing this way, and then it splits between R2 and R1. Next, I'm going to perform a current divider to figure out how much current went through R2. Remember that the numerator of your current divider has to be the combination of both parallel paths, which would be 50 ohms. And then the denominator has to be the value of the resistance you want the current for, which is 100 ohms. So in this case, I get that the current through R2 is 16.65 milliamps, and again, that's going down. Our last step is to add the values for the current through R2 together, taking each value from step 1 and step 2 and adding them algebraically. That means I'm going to consider the direction. Since they're both flowing down, I can simply add them together for a total current of approximately 50 milliamps flowing down. Again, as you do these problems, you must reflect the direction of current in every step and reflect the direction of current in your final answer after you do that algebraic sum. Now let's move on to another problem. In this problem, we're again going to find the current through R2. Notice that we only have 2 resistors, and this time we have a voltage source and a current source. So to begin, we're going to short the voltage source and find the current through R2. So here's the short. And now we basically have 2 resistors. These 2 resistors are in parallel. We know that there's 100 milliamps of current flowing this way, and then it splits. Some goes this way and some goes that way. So we need to figure out how much went through R2. You can do that using a current divider. So first I'll find the total resistance of these 2 resistors combined. And then I'll set up my current divider, where I have the total resistance on the top and the resistance of R2 on the bottom. Multiply by the 100 milliamps that's going into this node, and you get 68.75 milliamps flowing down. The next step is to put the voltage source back and replace the current source with an open circuit. So it looks like that. Basically what it means is the current that leaves this voltage source comes here and then flows right down here. There is no current flowing through this branch because of this open circuit. No current can flow that way. There's no path to take if this is open. So now I can find the current through R2 by finding the total current first, R1 plus R2. And then I can simply find the total current in the circuit by using Ohm's Law. These resistors are in series. They both have the same current, and that current is equal to the total current. The total current has to be 10 volts divided by the total resistance. So I get a value of 31.25 milliamps down for R2. Our final step is to add the values for IR2 from steps 1 and 2 together. Remember to consider direction. In this case, I got 2 currents that are both going down. So I can add them together for a grand total of 100 milliamps going down. And that completes the problem. Moving on to the third example, we now have 2 resistors and 2 current sources. One current source is flowing up this way. So this 10 milliamps is going to flow up and split. Some will go that way, some will go this way. This 3 milliamps is going down. Some will go this way and some will go that way. So our first step is going to be to take one of the current sources and replace it with an open circuit. Now we're going to find the current through the 100 ohm resistor. Keep in mind that this is an open circuit, which means the current in this circuit is going to flow this way, and all of that current is going to flow this way. No current can take this path because this is open. So there's no current flowing through the 56 ohms. All of the current is flowing through the 100 ohm resistor. We can also see that that current is flowing down through the 100 ohm resistor. Next, I'm going to put IS2 back, replace IS1 with a open circuit, and find the current through the 100 ohm resistor. In this case, the current is going to flow down and around like this. No current can take this path. That's an open circuit, so the current will not flow that way. And we can see that 3 milliamps of current is going to flow up through the 100 ohm resistor. And our final step is we're going to combine these together. Add the values from steps 1 and 2. Don't forget to consider polarity, because this time we had 10 milliamps down from our step 1 and 3 milliamps up from our step 2. We have different polarities. So when you have different polarities, what you're going to do is subtract them. Start with whatever one is bigger. The 10 milliamps is bigger. So start with whatever is bigger, subtract the quantity from the opposite direction, and then write your final answer. 10 milliamps down minus 3 milliamps up will leave you with 7 milliamps going down. It's really important that you know that direction when you finish the problem. And that completes this problem. For the last problem, we're going to find the total current through R3, again using superposition. Take a look at what you've been given. We have two voltage sources. The polarity is shown here, so we know with this voltage source, current flows down, and with this voltage source, current flows down. Keep in mind that's important. You must pay attention to polarity at all times. So let's begin using superposition. I'm going to start by replacing VS2 with a short circuit. And remember, my goal is to find this current right here, the current through R3. So we're going to start by finding the total current in this circuit now that VS2 has been replaced with a short circuit. Look closely at what you have. We have R1, which is in series with this combination right here. These two things are in parallel. I'm going to combine them together with this piece right here, and that combination is then in series with R1. So my total resistance, once I plug in all my resistor values, comes out to be 1.69 kilo ohms. Next, I can use that value to find the total current. The total current in the circuit is 11.8 milliamps because I'm going to take the 20 volts and divide by total resistance. So I know that 11.8 milliamps comes right down through here and then splits. It's going to take two paths. We need to figure out how much went this way. So I'm going to set up a current divider to do that. The numerator of the current divider must be the parallel combination of these two parallel paths. Combine these two in parallel, you get 687.5 ohms. The denominator of my current divider has to be R3 because that's the current I want to find. And multiply by the total current going into this node. So you get 3.69 milliamps going down. That's step 1. Step 2 is going to begin by putting the second voltage source back and replacing the first one with a short. And now we're going to find the current through R3. Notice that now the current through R3 does flow up. It's in opposite direction. Remember, that will be important later. Now I have to find the total resistance. This is where it might be a little bit hard to see, but let's trace the path of current. If we look here, current splits. Here's one path. Here's the other. Remember, our definition of a parallel circuit is the fact that current splits, takes two or more paths, and then recombines. The current splits. Here's path 1, here's path 2, and it recombines right there. So R1 and R3 are in parallel. Once I combine R1 and R3, they're both, as a combination, in series with R2. That's where I get this equation for total resistance. Once I plug in all the values, I get 1.69 kiloohms for total resistance. Again, do not assume the total resistance will always be the same in every case. Every case will be different. You must figure out what's in series and what's in parallel and find the total resistance that way. Don't assume it's going to come out to be the same, just because in this problem it happened to come out the same. 1.69 and 1.69. That's coincidence only. Don't assume that'll happen in every single problem. Now that I have the total resistance, let's find the total current, which is going to be the voltage for Vs2 divided by our total resistance. And now I have to find the current that goes through R3. I can do that with a current divider. Keep in mind, the two paths for my current divider are this one right here and this one right here. So the numerator of my current divider is going to be the parallel combination of those two paths, R1 and R3. We're going to divide by the value of R3 and multiply by the total current going into the node, and you get 2.78 milliamps going up. Our last step is to add our values for IR3 together. Don't forget to consider polarity. So we had 3.69 milliamps going down from step 1, 2.78 milliamps going up from step 2. So when I subtract those, because they have opposing polarities, we get a total of 0.926 milliamps going down. And that is how we apply superposition to a circuit that has multiple sources. Keep in mind that there are practice problems posted online for you to practice this concept. I highly recommend that you go through those problems because every one is different, and how you apply the theorem will change depending on if you have two voltage sources, two current sources, a mixture of each, etc. So make sure that you are practicing the superposition theorem, and we will get to demonstrate this theorem when we do lab 6 for the laboratory exercise. So you will get to see this firsthand in the lab as well. And that is the end of this video.